Harvard here for today's colloquium talk. Dr. Tarokh has many diverse talents, and most of all I'm happy to have him here because he's a good friend. And I've known him for some 5 or 7 years, but apart from that, he received his PhD from the University of Waterloo in '95, and then joined the AT&T labs in Maryhill, and then moved to Florham Park. He first was member of technical staff, then principal member, and then the last step in his career in AT&T was department head of wireless communication before he moved to MIT in September 2000. He spent 2 years at MIT as an associate professor and then moved to Harvard. So it's the same location geographically, different school, where he's a full professor, Department of Engineering, Division of Engineering and Applied Sciences at Harvard. He's presently a Gordon McKay Professor of Electrical Engineering and Vinton Hayes Senior Research Fellow. He has a large number of awards, honorary doctoral degrees. Arguably the most prominent is the Alan Waterman Award of 2001, which puts him squarely into the most prominent line of researchers and innovators in the United States. For me, the hero in that line of people who got that award is the, what's his name now, escapes me, the super string theory guy at Princeton.
What's a hero? Do you remember?
I need the thing you said, we can put the brain here. Whitten, Edward Whitten. Yeah?
Yeah, he did it.
Right? And he got it in 80 whatever, but he got it in 2001. There are many more prizes listed here, so I'm happy to have more.
Well, thank you very much, Sasha and Prakash, for Professor Vahid and Professor Narayan for inviting me here. It's a pleasure to be here. And thank you for being a friend all over these years. I'm glad to be here. So today I'm going to talk about essentially developing universal algorithms and associated speed-up calculus for tracking of fluid policies in input-queued switch networks. This research actually is motivated by some of the guys here. A paper by Kabatabari and Sealers actually kind of led us to work on this problem. And to give the credit to the right people, Michael Rosenblum and Raymond Yim and Konstantin Kamanis are the students that worked on this problem. And I and Michel Thomas essentially supervised as a student, so it's mostly their work. So first I give an introduction as an outline, and then I talk about fluid policies, and then packet policies, and then I talk about tracking of fluid policies by packet policies. And we'll talk about briefly about input queued and output queued crossbar switches. And then I'll talk about some results that we have on crossbar switches. And then I'll talk about switch networks, namely Banyan network. And there I could show that a speed up becomes a factor when you deal with networks of switches. And then I talk about our results there, and finally I conclude. Since we actually talked about, since we wrote this paper, there has been 5 or 6 more results that these young students did, and I'm not presenting them all because it will take 2 to 3 hours. But quite a group of creative people. As I said, it's mostly their work. So let me first start by just an introduction. Well, I would say that perhaps packet networks are the most influential technological advance of the 20th century, and even early 21st century. I mean, the string theory is great, but everybody's on the internet. So the fact is very clear. I mean, just go and look at ATM networks, or you look at internet, you see how successful they are. And if you look at how these things are started, you see that there has been a lot of R&D efforts in this field that led to a lot of activities on networks. And there has been a lot of progress, of course, even since the time of Davis, Wilke, and those guys, and networks and switches. But in my opinion, still the theory of packet networks have a lot of room for development. That's why we actually got into this field. I mean, Michel is an optimization person, and I used to do communication. So let's talk about these networks. When you talk about packet networks, you will see that dealing with packet networks is generally much more difficult for analysis than circuit switch networks. Because you have a discreteness in it, the packetness essentially creates all kinds of problems. So what you do is essentially, traditionally, people pick up some continuous approximation to packet assumption, and then they apply this continuous approximation to the network. They get some result, and they assume that that result will for the discrete case. Sometimes they're right, and sometimes they're wrong. But this is just the way that people analyze it. So, in one of the approximations that is common, packet traffic is approximated with the flow of a fluid. The discrete nature of the traffic is approximated by continuous models. So this is so-called fluid assumption. And I looked at the literature because I'm kind of myself new to this, for 2 years I started looking at this kind of topics. And a number of things that I looked at, and definitely non-exhaustive set of examples that fluid policies are used, are for instance in papers about weighted fair queuing by Demers, Peshav, and Shenkar. If you look at, for instance, recent works that people looked at analysis of the stability of TCP with AQM methods. Dan Housley and Jonas Amherst and Bond and Sally Floyd, Lowe and Lapsley, these guys all use this fluid model to analyze around the equilibrium point protocols and their stability. And then, look, we could also talk about how the people analyze new protocols that integrate UTP and TCP flows over the internet. For instance, CHOPE is a protocol by Balaji Prabhakar that he analyzed it using fluid models. So sometimes fluid models being analyzed protocols with don't give the right answer when you simulate, but people use it. And one other example, which is quite by itself a field, is what Kelly did at Cambridge. Kelly looked at the old works of Gerard Debreu and Aroff on economics theory, equilibrium theory of economics, and applied those models using fluid policies to flow controlling networks. And there's a whole field called pricing coming for networks coming up with this. So what is the goal of our research? Our research is about figuring it out that if you're given a switch network, arbitrary switch network, what kind of a time-varying fluid traffic you can send from the n input points to the m output points that can be approximated by packet traffics with bounded delay. This bounded delayness is very important. I mean, statistically, people analyze switches. They usually prove the results of this kind of the buffer size is with probability 1 bound. This is the kind of things that probabilistically prove. Now, if we try to approximate packet policies by fluid policies and then analyze and come up with concrete bounds, not infinity or finiteness with probability 1. But as a matter of fact, like a real concrete bound that shows how much backlog you need in a switch, and then come up with concrete schedules for doing it. Of course, when you deal with a switch network, you have to look at the components. And also, how fast these components operate, what's their speed up. So along the way, they have to develop a speed up calculus. And that's another kind of distinguishing point of this work that is students, if they actually look at this problem all in conjunction with each other. And then you could also look at concepts like look ahead, meaning the delays that you could tolerate, and all of the trade-offs that are involved. And I would say this is an important problem because essentially you want to know what kind of a short-term average of admissible traffic you could accept into a network, a switch network. So therefore, this problem, at least theoretically, is of interest. I'm not saying that I'm going to show today is practical. So, in theory, if you give me a switch network and tell me what traffics can you accept into this, admit into this network, the answer is that I don't know. But because we don't know the answer to a general problem, we can focus on some concrete problem that people know about it for a long time and see what can we say about these simple examples. One example is the input queued crossbar switch. The other example is the Banyan network. These are examples that I'm going to deal with today. So, what's the input queued crossbar switch? You have an n by m input queued crossbar switch defined as a box that has n input and m output. So now all the data cells that go through the switch, we assume that they have the same size, namely 1 unit. And at each point of time, one port of input can be connected to one port of output, and no two inputs can be connected to the same output. And this is essentially the assumption of switch. And moreover, we need to have some virtual queues at the input, meaning that if you are looking at some port, all the packets that are destined to each one of these m output ports are going to put in m different queues. So you don't have so-called head-of-line blocking. And that actually, in theory, can give you 100% utilization. There is a paper by Nick McCoon that is at Stanford, and he shows simulations that in some examples that with Bernoulli arrivals of some kind, he shows 100% throughput. But can we actually deal with any traffic and not really just the specific statistics and so on? So as I said, we assume that no two input ports can be connected to more than one output port and vice versa. And as I said, at each time, each link carries at most one packet. So we can define a matrix. The matrix is an n by m matrix where the I and j element at time t is 1 if the input node I is connected to the output node j. If 0 otherwise. So what this condition of switching means in an n by m switch is that you have this sub-permutation matrix. And only packet schedules corresponding to sub-permutation matrices are valid for sending packets to switches. So we define a packetized policy, a sequence of admissible packeting schedules, meaning that a sequence of n times m sub-permutation matrices, which are denoted here by p sub k, for k greater than 0, where k is the time axis, representing the whole packets sent over an n by m switch at each time step. We define a fluid policy to be a sequence of n times m doubly substochastic matrices. F sub k, which I denote F standing for fluid and P stands for packet, k time. This represents the fractional packets over an n by m switch that can be sent at each time. So if we assume that the packetization was not the barrier, these would be the things that could be admitted. So we define a number of notation in order to present the result. To begin with, we look at the input port I and output J, port J, and we record the cumulative number of whole packets sent by the packetized policy up to and including time k. And then we look at all the fractional packets sent by the fluid schedule up to the time k, the sum of them. And then we take the difference. This difference is how much a schedule that is complete, the packetizing schedule, is lagging or leading a fluid schedule, which is kind of an abstract schedule, what could be a schedule very easy. So if you look at our definition, we see that by infinity, first of all, at time 0, there is no backlog, so we got C naught equals to 0. At time k, what you have between the commutative differences is what you had at time k minus 1, plus the fluid that came at time k and the packet that left at time k subtract. This is essentially just bookkeeping. So let's make an example. Here I have a sequence of fluid policies, and here I have a sequence of packets, packetization schedules. So what we have here, we could actually look at the amount that the commutative number of packets sent under this policy and under this policy lag each other. And for instance, here you subtract this from this guy, you get this matrix. At time 2, you subtract the sum of these guys from the sum of these guys, you get this matrix, and so on. So what we want to know is, if somebody gives us a fluid policy, can we make a packetized policy such that the aggregate number of positive elements here per se is bounded subject to some constraints. That means that however you can actually approximate the general fluid policy from n by n crossbar switch with a packetized policy. And then we want to find algorithms that actually minimize additional backlog, meaning that the measure of additional backlog could be maximum of all the positive elements in the backlog matrix, or the sum of positive entries in backlog. And for the purpose of defining what this approximation means, we have to formalize the definition of tracking. These definitions are not due to us. They're due to other people, and we just picked it up from the literature. So a packetizing algorithm is an algorithm that takes a fluid policy as input and outputs a packetized policy. The catch is that the packetizing policy cannot send any packet until some portion of the packet is sent under the fluid policy. That means you cannot service when you are not given guaranteed packets. In terms of our normalization, it means that the backlog matrix C sub k, all the elements have values greater than negative. We say a packetizing algorithm is online if it doesn't need to know the future in order to output the packetizing schedule. So to compute the packetization schedule at time k, you only need to know the traffic at time 1 to k, all the past and present traffic. But you don't need to know about future. So we are not interested only in online algorithm. So now this definition is due to Tabatabai and Tessiris, and they actually defined a packetizing algorithm to track a fluid policy. If for any given fluid policy, it outputs a packetized policy such that whenever the fluid policy services a packet, the packetized policy also services. That means that all the elements of this commutative difference matrix have to be less than 1. So we want, somebody gives an arbitrary fluid policy, we want to make matrices such that these commutative matrices, all of the elements are between negative 1 and 1. That's what we meant by that. So the question that actually Tabatabai and Tessiris, and perhaps other people before that, which I don't know, might have asked, is that is there any algorithm which tracks an n by n fluid policy for the n by n crossbar switch? And Bonacelli and Clo and Tabatabai are the few people that actually know what Tessiris that actually work on it. And if it is not possible, is there a way that we can quantify how well we could approximate this lagging of the packetized policy from the fluid policy? How much buffer size? And moreover, we want to find algorithm for that. We want it to be algorithmic. We don't want to just prove theorems that don't give you an algorithm, are not constructed. So here is a list of some people that have worked on this problem as far as I know, and the literature stage. One is of course generalized processor shading and packet-by-packet generalized processor shading. These concepts are for the n by 1 switch. They were introduced by Demers, Keshav, and Schenker. And if you look at the general fluid policy, means time-varying one, here the fluid policy is that the fluid schedule is constant. The time-varying one, we found it in the works of Duffield, Lakshman, and Styliadis, and Stamoulis and Giannakis. But there could be other people before that they considered, I don't really. For constant fluid policies on n by n switch, Chang worked on this problem. He came up with the so-called von Neumann group of switches. Now, it could have been before that used in 70s on satellite literature by other people, but I don't remember exactly who is the first one. These are the people. And the case of general fluid policies on n by n switches, as far as I know, it was looked by Bonacelli and Clo and Tabatabai, Georgiadis, Tessiris in 2000. Now, Bonacelli and Clo proved that if you have an n by n switch, For n greater than 4, you cannot track the fluid policies using packet policies. Tabatabai and Tessilos showed that for 2x2 tracking, 2x2 switches you can track. That means tracking algorithms exist. Actually exhibited constructively such an algorithm. Actually, that's what motivated our application. And the construction of Bonocelli and Clow shows that for any n by m input queued crossbar switch, if either n or m are greater than 4, either n and m are greater than 4, both of them are greater than 4, or 4 by 3 also. You cannot find a fluid policy that cannot interact. So for 4 by 4 and anything above 4 by 4, 4 by 5, 5 by 4, 5 by 5, you can't track. 4 by 3 and 3 by 4 also turns out you can. Actually, as our first part of this work, we classified all the switch sizes.
For any buffer size?
Yes, I'm getting to that. For any buffer size, you can track any fluid policy. That's the result I'm going to present.
So what's the constraint of the first fluid?
There is no buffer.
I mean,
yeah. Okay. So the tracking is just means that you have at most at each time every element between 1 and -1. That means that essentially very little buffer is. Okay, so therefore, as we saw that one of the audience pointed out, it's a negative result, which is awful. So it motivates that you study packetizing algorithm that satisfy a relaxation of the tracking concept. Meaning that you should actually throw the concept of buffer into this problem. That's what we do. So here we define the backlog that is the concept that we have to have in order to put everything in the same way. So we define the backlog at time k at an input port I to be the sum of the positive elements in row I of the matrix that actually tracks the differences between commutative differences between fluid policies and packetized policies, the CK. And if you have a set S of input ports, we could define the backlog to be the sum of backlogs of all the elements at time k, in that sense. So the total backlog, therefore, for the whole n by m switch, will be the total backlog of all the ports of the switch. It will be the total sum of all the positive elements of CK. So backlog quantifies how much additional buffer size you need in order to track. So we discussed this. Okay. We say an algorithm is B backlog, meaning that we can come up with if we can come up with a packetization algorithm that at all time the total sum of all the positive entries of CK is at most B. At all times. Never ever the queue sizes go above B. And as I said, usually people in probabilistic methods, they look at queuing in literature from probabilistic point of view. They look at these results from probabilistic point of view in the sense that they say with probability 1, the queue sizes are finite under such an assumption on the arrival distribution. What is the point of departure here is that we use this generalized idea of tracking to show that any fluid policy can be switched with 100% utilization. And we bound the underlying queue sizes irrespective of the input. So no matter what the input is, as long as it satisfies the stochasticness condition, you would have this result. So first I'm going to present the results for the n by 1 switch, which is the most popular switch that has been studied in the literature. Here I define the greedy algorithm, the packetization algorithm that actually services the port with maximum positive backlog. And also I need some notation, harmonic series. H sub I is the sum of 1 over I, 1 over k, for k going from 1 to I. And I define this function g of m to be the summation of I equals to 1 to m, h of n minus 1 minus h of I. So this turns out that we could prove the following. If you have an n by 1 crossbar switch, doesn't matter what packetizing algorithm you design, as long as it's online, you could come up with a fluid policy that makes the sum of backlog in a set of m elements of the input port greater or equal to G. That means that there is a concrete limit that you cannot reduce your backlog for any m. So particularly when m equals to capital N, you get G of n, and then you can bound that by log of n minus 1, or by n over e minus 2. And for one port, you can bound it by log of n minus 2. So what we have here is that we have a lower bound, but that doesn't mean that we can concretely prove that the backlog can be upper bound. Let me just give you an idea of this. Proof before heading to the other side. If somebody gives you, essentially this is kind of like a worst case fluid policy. Nature, which would be the packetization fluid policy, and you, which would be the packetizing algorithm, the switch, are playing a game. So here I got the nature giving me this fluid policy, and if you want to packetize, you don't know what's going on in future. So for this policy, you have to just clear one of these elements. And you do. Now nature knows that you clear one of those packets and you got a negative 450, right? So what it does, it says, okay, I'm going to divide all my resources between ports that has not been serviced. And it puts all one port in all the other nodes as that. Now, again, you don't know, to you all of these nodes up to now looks the same. You have to service one of them, so any arbitrary one you service. So then nature comes and throws its power between the nodes that you didn't service. Again, it all looks the same, so you service one more. So
Does this algorithm have memory or not?
this algorithm doesn't have any memory. Just looks at
The choice is instantaneous?
it's online. It's online.
Yeah, but
Meaning that the past is looked at.
The past.
Yes. You're allowed in making your packetized policy to look at the past.
But not in this example.
In this example, you are looking at the past in the sense that you see what was serviced.
Just that.
Yeah. So here, this example is the key to our proof. Essentially, we make this thing in notational format, and then you could see that, for instance, in this example, we got the positive elements are actually the sum G of n that is. So that's essentially the idea of the proof of the lower bound. Now, it turns out that this lower bound is tight, meaning that it is actually equal to the upper bound on this. The greedy algorithm always gives you exactly this upper bound, which is equal to the lower bound. That means that for any fluid policy, the greedy packetizing algorithm produces a packetized policy satisfying exactly the reverse inequality. Which means that the greedy algorithm, in the case of n by 1 switch, not only interacts with this bounded backlog, but also is worst case optimal. That's the result that we prove. And the proof of this thing is actually technical, but very elementary. I mean, it's heavy, but elementary. And of course, it's constructive because it gives you the greedy algorithm. Turned out that after we did this, we looked at the literature, and in another completely independent literature on databases, there was a guy by the name of Mika Adler, and he had this result. So that was not normal. So,
What year was that?
it was just last year. So just at the same time that we did this paper got published in a conference. So these things happen. But independently, completely independent literature. And Mika used to be at AT&T, if you remember. He came for a visit. And then he left and went to UMass Amherst. So a lot of good people at UMass Amherst. So now, what about the n by n input queue solution? Now, of course, you could say take the n by n switch and take the n input ports and one output port of all this n by n switch. You have an n by 1 switch. And then you could, of course, apply the results and get a lower. A lower one means nothing if you can achieve it, right? I mean, that's the whole. So can we come up with an upper bound on backlog and n by n case? Now, there are two major obstacles in applying the method of the proof of the fact that the greedy algorithm is worst case optimal in this case. First, it's not clear what is a greedy algorithm, because you cannot allow any full matrix at any time, essentially. So if someone may say, okay, do the maximum bipartite match. We tried to do that, but I mean, you couldn't come up with results using it. The second obstacle is that sometimes you can even send the full permutation matrix if you want, because the ports that you want to service, both need service, they may be going to the same destination. So in fact, it's not clear at all that the backlog can be kept finite. We know that if the buffer size is not there, it cannot be kept finite. That was the result of Monticellian code. So we need to introduce a new notation, a new machinery to address this now. So this is the result that actually Mark and Raymond and those guys do, and is motivated by von Neumann and Birkhofer. What it says is that there exists a factorizing algorithm for the n by n input switch, n by n input Q crossbar switch, that is at most backlogged by n minus 1 to the power of 2 at per input. That means the total backlog is n times this, at most, regardless of the time. And not only this result is true, but the proof is done by explicitly providing the packetizing. Now, I cannot prove the whole thing for you, but I'll give you a description of the algorithm, because what they did is really astounding. So, first of all, the algorithm, in order to describe it, the algorithm is online. What it does, it looks at only the commutative matrix of the difference between packet policy and fluid policy at time k. Look at what comes in at time k plus 1. In terms of fluid policy, it outputs p sub k plus 1, the packet policy at time k plus 1. So therefore, I don't even need to deal with the subspace, because the algorithm I'm going to do only depends on values at time k plus 1 and k for the output at time k plus 1. So I drop the k's. So C is C sub k, P is P sub k plus 1, and F is F sub k plus 1. The algorithm maintains the following invariants at all time steps, that the sum of positive elements in the matrix Ck for each row is at most n minus 1 to the power of 2. And the whole matrix, the sum of all the positive elements, is n times this. If I can prove that the algorithm I'm going to construct always maintains this invariant, then the theorem is true. So, of course, at time 0 it does. So, inductively I press. There are 3 steps. First, at time k, the matrix C is given to you, and you know that by inductive hypothesis, you have all the positive elements sum up at each row to n minus 1 at most. If the fluid policy that comes in is a substochastic matrix, so the sum of each row is at most bounded by 1. So C plus 1F, the sum of all rows and all columns, are exactly bounded by n minus 1 squared plus 1. Now, there's a bound. What we are going to do, we are going to construct a matrix B with all positive elements such that C plus F at each element is less than the corresponding element of B, and you have the sum of element of B exactly be n minus 1 squared. Then, that's the first step. Then we go and look at matrix B. And we see what elements of B have value greater or equal to 1. And if they have value greater or equal to 1, we make them 1, otherwise we make them 0. Now we find the permutation matrix that is dominating. And thirdly, we look at the sub-permutation matrix of this permutation matrix by keeping those elements of pi for which you have some traffic to clear. That is the arrow. And now I have to show that this thing actually works. Well, the invariant property, as I said, at time 0 is true. Now, assume that this algorithm is well defined up to the time k. Now, we are going to show that everything will be well defined at time k. Well, by invariant property, the sum of all the positive elements of each row and column of C are dominated by n minus 1. Thus, the sum of all elements of each row and column of C plus F are dominated by n minus 1 squared plus 1, all the positive elements. Now, there's a theorem, so-called von Neumann theorem, that is actually due to Koenig, not von Neumann. And it says that any substochastic matrix can be dominated by a stochastic matrix. And it's actually a very trivial result to prove. Now, it's von Neumann-Birkhoff saying this part is attributed to von Neumann and the other part is attributed to Birkhoff. But the results both are due to Koenig. So, or Koenig, because you know better, because you're from Eastern Europe. So what happens here, the pronunciation is right. Now it follows that C plus F can be dominated by matrix B with non-negative entries, with the sum of all rows and elements exactly equal to n minus 1 squared. Now we apply the result of Birkhoff, which is due to Koenig. So, the Koenig theorem says that any substochastic matrix can be decomposed into the weighted sum of n squared minus 2n plus 2 permutation matrices. This is nothing but Krateodori theorem, if you really think about it. Of course, the difference is that Koenig gave an algorithm that was real time. I mean, it's polynomial. But I don't know personally of any algorithm for Krateodori result is polynomial. So, therefore, B can be written as sum of n minus 1 squared plus 1 permutation matrices with all positive weights. Because B is n minus 1 squared plus 1 times a stochastic matrix. So we apply this. Well, now we look at the sum of elements of B, and then we look at the sum of all the stochastic elements that are there, and we conclude that one of the coefficients has to be greater than. That is the permutation matrix that we decode. Just by looking at the sum of elements of B, is this much. Then there are n minus 1 squared plus 1 elements. So one of them has to be greater than 1. And that is what it is. Now, from the way that I constructed B, C plus F was dominated by B. So now we are going to restrict pi to those elements that we have something to clear, some traffic to clear. And we are going to show that this relationship holds. And that checks very easily, because you only have to just do some add. So that essentially proves the first upper bound on the required buffer size and a constructive way of achieving it for any time in varying fluid traffic that can go through an n-minus switch with 100% utilization. So the algorithm, of course, the von Neumann part of the Koenig algorithm, does order of n squared. But the Birkhoff part is more complicated. It is order of n to the power of 3.5. The fact is that you could do a simpler thing, so-called bipartite graph matching, that is due to a striver. And you could do order of n to the power of 2 to 2.5. But if it can be reduced again. And I must say that the above ones are conservative, because we're allowing the traffic to change slowly and not arbitrarily. In practice, the long-term average or short-term average of the traffic over a long time doesn't change so drastically. It's just slowly time varying. This property may be used perhaps to further reduce this bound by introducing some form of L1 metric, the difference of the fluid.
I made a visit, but I have to ask one question.
Sure.
Have you shown that if you increase the memory of the algorithm, that you cannot reduce the buffer?
What we showed is what we could talk about. I mean, definitely there is a trade-off between look ahead and the buffer size. For n by 1 switch, recently one of my students, his name is Raymond Yim, one of the authors here, he came up with a complete trade-off calculation between buffer size, look ahead, and speed up. That's a new result. He's actually presenting it in a conference very soon. But for n by n, we are very far from having such things. So we don't have, I have no answer.
So the structure of the algorithm that accepts CK and FK plus 1 is an output PK plus 1 comes from where?
It comes from our limitation arithmetic.
Of the proof.
Yes.
Okay, all right.
It comes from the fact that we are not. Okay. So, and now let's look at the case of n by m case. We could mimic the same thing and apply Krateodory's theorem and prove a similar result. Because what is big up part of conic theorem is actually Krateodory theorem simplified. But then the algorithm is not polynomial. Now let's talk about more complicated switch networks. Now, if you look at any internet switch, they put all these little 2x2 switches together and they make huge switches called Banyan network, for instance. And they make switches from a small switches, many other constructions. So, of course, there is a trade-off because these switches have modularity, parallel capacity, efficient construction, expansion, etc. But would that make it more difficult for them to actually switch the traffic? Would that reduce the utilization? That's the question that we want to ask. So we look at Banyan networks because, again, because of the fact that we are not good, I can only do this a small example. If you give me an arbitrary switch network, I have no answer. This is a Banyan switch made from 2x2 switch elements that are put together in this way. Now let's make it even easier. Maybe I go for another video because this is easier to see. If you want to send from link 1, from input port 1 to the output port 1, and if you want to send from input port 2 to output port 1, or input port 2 to the output port 2 at the same time, you can't send it at the same time because what happens is that all the traffic from 1 to 1 and 2 to 2 has to go through link 5. Right? So you see that here there is a restriction of what kind of a packetized policy can go through this switch. That is what makes it a little bit more difficult to have. Essentially, indeed in a Banyan switch, you have log 2 of n stages in n by n minus switch. Always n is a power of 2, and there is a unique path for each input and output pair. That's why they use it. They look at the binary expansion of that rest, and they could actually rotate. So, what happens is that if you send from I to j, there could be input-output pairs k to l that they share an edge in this whole path, so they block each other. So a valid one-time permutation in packetized policy is a sub-permutation matrix that requires that each underlying link is only used once. So you could not have 1, 1, and 2, 2, both to be one in your permutation. That's the point. Okay? So let's visualize this graphically because that makes it much easier. You make a graph. The points of the graph, the nodes are pairs of input-output pairs, I and j and k and l. So if you have n input and n output, you have n squared nodes. Two nodes are connected together if if you want to send from I to J and K to L, they block each other. So whenever they block each other, you draw an edge between those two. And this graph, essentially, we call it the link graph, gives you all the underlying constraints that exist in the switch. Essentially, a fluid or packetized schedule is valid if the summation of the elements of the matrix Xij over all the clicks, meaning a complete graph. Q, for instance, any click that you pick up Q, the summation of all the corresponding elements have to be less than 1. Meaning you can only send one packet, because others get blocked.
Does this hold for general graphs?
I'm sorry?
Does this hold for general graphs?
Does it hold for general graph? You can define this thing for a general n by n switch. What is the question? For any arbitrary network?
Yes.
I could define this graph for any arbitrary network. And it is in fact not me that can define this. This is done by Lovash in other context. And navigate actually. So we have this graph. I didn't draw all the lines because it would be too much traffic. The whole point is that, for instance, port 1, 1, 1, 2, 2, 1, 2, 2, all share one link. So therefore, they make a click. Now, neither both the fluid policy and packetized policy, they have to sum up to 1 over these ports. That means, for instance, the traffic F11, F12, F22, and F21 have to be less than 1 and so on. And so similarly for the packets. Only one packet between these four. Now, the sure result, the speed up is required. Let's look at this traffic matrix for the 4x4 band network. You see that this fluid policy as a whole sends a total of 4 packets at each time through the switch. Because you add them up, all the elements add up to 1. So if this is a constant fluid policy, we let it just be always this way. It's an infinite looker. The switch knows forever that this traffic exists. Now let's look at any packetized policy that you could send through the 4x4 bandwidth switch. Say here you send 4. But any packetized switch, packetized policy that you put, for instance, if you send a 1 in this location, it eliminates all the possibilities of being sent here, here, and here. Because these are all connected together. So once I put 1, 1 as 1, I have to make sure that 1, 4, 3, 1, 2, 2 in this picture are not sent. Because the rest of them are essentially 0 anyways in aggregate. There's nothing to send. So 1, 4, this guy and this guy. Now, if you pick up another element, say 2, 3, you will see that 3, 3 would be ruled out. And if you look at another element, say between 4, 2 and 4, 4, only 1 can be sent. If you look at all the possible ways of doing it with this fluid policy to packetize it, you will see that there is only 3 packets that you could send per turn. Doesn't matter. Start from any point. Because of the constraint, only 3 packets. So you are sending 4 packets through fluid policy, while the packetized policy sends 3 packets. There is no way to catch up. Yes.
How do you actually interpret the fractions in the fluid policy?
It is the long-term average. It's also called guaranteed bandwidth. But an ATM switch, we can think about the short-term average, which is longer, much longer than the switching time. Assuming that the traffic
The long-term average of number of packets that go in that direction?
in average number.
So they're like probability.
Not really that probability, because the traffic could be bursty and we don't know the underlying probability.
No, meaning
But there is a police check that guarantees that. So the switch has a circuitry that says, okay, I negotiate this much bandwidth, and I'm not going to allow any bandwidth from port to I to J to go around. Okay? In average. So what we see here is that, therefore, we need a speed up of 4/3. That means my utilization is only 75% for 4x4 binary switch. Now, this shows that it's at least 4. But we proved the following result, that actually the speed up required by the 4x4 Banyan network to track any constant fluid policy with bounded backlog is exactly 4 times. Now, to prove the other side is extremely difficult. And we didn't prove it. It is actually done by 3 very famous combinatorial mathematicians, combinatoricists, and it relies on a theorem of Claude-Birch. It was a conjecture of Claude-Birch. He conjectured a so-called strong perfect graph. And recently it was, after 5 years of work by 3 mathematicians, proved. So this is not trivial to prove that exact features. So now, if you look at n by n Banyan switch, we cannot really give you the exact speed. The only switch apart from crossbar switch that the required speed up is 1, that we know about, the exact speed up is 4x4 Banyan switch, and the exact speed up is 40. But for by n, we could bound it, and we have a result that the bound is log to n plus 1, and then if you have this one, the bounded delay, you could essentially route traffic with this much speed.
What is your meaning of elementary and difficult that you puzzle there? Difficult or elementary?
Which verb?
The second bullet, is it elementary or be difficult? So is it both? One or
Okay,
the other?
this elementary means that the mathematics is not fancy. Meaning that, for instance, you don't need to appeal to anything about high school mathematics. But it is difficult, meaning that producing the result is not trivial.
And what is the practical meaning of speed up here?
Means that you can have as much utilization that much. For instance, you have 1 over that. So from the above results, we actually learned that coming up with an exact speed up calculus for bounded delay tracking of fluid policies in an arbitrary switch network is difficult, because we could only give you 2 examples. However, if you want to do bounding only, we could perhaps do something, meaning that we could talk about the speed up of the switch network in terms of the components.
I'm sorry to go back on the way in the beginning, but I have to ask this question.
Sure, please.
Okay. The problem is what? That you're trying to use fluid policies because they're easier to compute and then you try to compute.
They are easier to schedule, and there's a kind of negotiated rate over a long time that you give to somebody. Sometimes it sends more, sometimes it
But
sends
then
less.
which is easier to compute? Because in the end, when you try to implement it, you only can implement packetized policy.
That is correct.
Right.
So over some time, you get this much guaranteed bandwidth to somebody. So you look at how much guaranteed bandwidth you gave to the guy. You don't want to sell him much more.
Thank you.
Okay. So this is a more modest goal, that if you want to just upper bound and talk about utilization rather than exact amount. And we're actually currently working. So now I'll conclude my talk here. First of all, in this work, we consider the problem of tracking of arbitrary fluid policies with bounded delays. For the n by n input queue crossbar switch, we derive a universal operand on the required buffer size and packetizing algorithm in order to track any time varying fluid policy with 100% utilization. For the n by 1 switch, we proved that our bonds cannot even be improved. That means that the greedy algorithm was worst case optimal. And in fact, we demonstrated an explicit algorithm that achieves the worst case. We then considered Banyan network as an example of switch network. We showed that the speed up was required for bounded delay tracking of arbitrary fluid policies in Banyan networks. The exact speed up for the 4x4 switch, Banyan switch, was computed to be 4/3. But upper bounds on other Banyan switches were computed, and that was the more general case. Nice time.
Nicolas, thanks very much. Overall, yes.
So, if in the fluid in one step, if you say half, then it would correspond to a stream of packets, right? Not just one.
Average of the stream.
Right. So then in the
High press.
packetized you can, instead of trying to match it with only one matrix, you can have a sequence of matrices, right?
No, in the packetized, you can only send integer packets. You cannot send fractions.
Right. But one step, because it's a
The
string.
one step you should think about it. The one step you should think about it as normalized. At one step of time could be, for instance, many steps of user of switch. If you assume that the traffic is constant within the
Right. So in the packetized also, you make your scheduling decisions at the same step in time. You
Yeah,
don't-
online, completely.
No, but you don't do it, say, I mean, if the stream was, say, 50 packets, right? If in the fluid one step sort of corresponds to 50 packets,
Okay.
then in the, you don't like do one permutation for the first 10 packets, another for the next 10, and so on.
Yeah, it's just assume that the time is normalized. And this is the worst case. I mean, obviously traffic doesn't change that drastically over time, right? I mean, because one dot switch time could be very, very small. If we assume that the time is normalized, even if the traffic nation average changes drastically, we should have a worst case bound, which is really worst case because, I mean, traffic, as I said, if you can say something about changes in the traffic slowly, you could improve it. But yeah, I mean, each time, we look at how much service we gave to the guy, we should supposed to give him, and then we come up with packets that track. Yes?
Can I answer the following question with this regard?
Okay, well.
Are there any fluid policies for which I get exact tracking, but it is a subset of general fluid policy?
A subset of generalized policy. This problem actually, I think, is done by Lovash, solved by Lovash in the context of a stable graph polytope, fractional stable graph
But
polytope.
because in reality you don't care about basic policies, right?
That is true. You see, what happens in the n by n switch case, the reason that this thing works is that permutation matrices are actually the extreme point of certain complex polytopes.
That's also very
Yeah, but it's not generally true. So Lovash actually came up with these two concepts, and you could bound.
But you can look at the minimal sort of permutation that spans a set of fluid policies, and that
Minimum, that yeah, you could restrict
You
your
can find
policy to be to certain.
you can find that, and then you can say for those fluid policies, now I can have exact tracking.
You could, but then you restrict the traffic that can go through them
No, you
as
don't.
much as possible.
That's the point. The point is that in practical networks, the policies, if you interpret the policies as allocation of bandwidth for pairwise users, are not going to be very strange.
You're not going to be very.
Strange.
They're not going to be very.
And your results are worst case results. You are
Yeah,
looking-
sure. In practice, of course, I mean, in practice, you could even perhaps reduce these bounds drastically.
If you look at, for instance, your early results reported of the impossibility results,
Yeah.
these policies are pathological.
Oh, yeah, they're all
That's
pathological.
what
That's
I'm
true. Fair enough. I mean, these are worst case bounds. I mean, in general, there is lots of ad hoc algorithms that do much, much better than these bounds
Yes.
because they're just worst case.
Now let me ask something else. Why I cannot take a fluid policy, which gives the interpretation of the average bandwidth, and switch the interpretation in the sense that now I'm going to send the packet through that path by flipping by getting an atomized algorithm.
Yeah, you could perhaps do that. So, but like, how would you guarantee that the backlog would be bounded? Or
No, I don't know if I can guarantee it, but I
Yeah.
can interpret the fluid
sure,
policy
you
that
could do
way.
it. I mean, yeah. I mean, there are lots of randomized algorithms in this context. I mean,
Right.
people have studied randomized algorithm for switching. But the whole point is that you have the results that they generally prove is that with probability 1, the backlogs are bounded, above. You don't even give it the exact one. I mean, if you can prove such a thing, of course, that would be the same.
That raises the following question. Whenever you have zeros in the fluid policy, you have a zero in the packetized.
Right, so there is no packet to be
Right.
sized.
So which means, when you look at the difference between the matrices in a certain sense, these are stochastic matrices, right? So you can define the notion of distance between them. In fact,
Sure.
one is a variation of distance. sort of proportional to the value being discussed. So it is bounded above by the divergence, and you can use divergence minimizing algorithm to approximate the fluid policy by another one which has ones and zeros and find a bound on it, and that will put the existence.
I don't know anything about variation algorithm, nor about the approach that you're proposing. I mean, it perhaps could work. I mean, just what I knew at the apart.
I understand what you're saying.
Yeah, it is possible. I mean, but perhaps, I have to read about it before I can say if I'm comfortable. But I mean, it's an idea. I mean, there are many things that you could do. The point is that can you actually prove concrete bonds in any case?
No, because
Yeah.
the probabilistic interpretation is just a tool. That you're not doing anything probabilistic. In other words,
Sure.
you have those matrices and you're trying to find bounds on some distance between them. And you're giving probabilistic ideas to get the bound. But the bound is a hard bound.
I really don't know, but I mean, it would be good if you show me on paper.
More questions? Thanks very much. So the plan is to have a roundtable discussion.